Hello everybody, this is Cameron Snow with Danomics.com. So in this video, we're going to be doing another Danomics basics lesson. In this lesson, we're going to be looking at clay volume and the different ways we can calculate that. All right, let's get started. So in our last lesson, we had just finished up with getting our data interpretation ready, and now we're ready to start that interpretation. And the first part of most petrophysical interpretations starts with trying to understand the clay volume. So we're selecting the clay volume module here within Danomics. And there are a number of methods that we can use to calculate clay volume. There are what we call single clay indicators, so things like gamma ray and SP that you're probably quite familiar with. And there's also what we call the dual clay indicators. These are methods like V-clay from neutron density, neutron sonic, sonic density, etc. So I want to demonstrate to you how we can use one of each of these in calculating our clay volume. So there's always a question about which one to use and which one to use first and how we can calibrate this. Well, I personally like to use the V-clay from neutron density as my first order interpretation. And the reason why is a couple of different reasons. So first of all, when you look at the neutron density log, you can look at the separation that are between these two curves, and that gives you an idea for how clay-rich a formation is. Also, when we look at a cross plot of neutron density, we can see where the various clay endpoints are, and this is something we can calibrate because this has all been very well modeled. So we know what an illite, a smectite, a kaolinite, etc. looks like. We also know what sand, lime, and dolomite look like. So we have a very good idea of where to set our endpoints. However, with the single clay indicators like gamma ray and SP, there are a lot of things that can affect those. So for example, gamma ray can be affected by some of the trace elements that have a bit more radioactivity. It can also be affected by tool calibration. And with SP, of course, that's a method that looks at essentially permeability, but it can also be affected by the mud composition relative to the fluid composition. So it's something that needs to be calibrated to another method. So first of all, let's get started with our V-clay from neutron density. So what it is we do here is we decide on a matrix point. So here you can see I'm moving this point here, and that is my matrix point. Now we will customize this zone by zone, but at first I'm just going to drop this on a sandstone matrix. I'm also going to take this point, and this is what's called the clean one point with the neutron density, and I'm going to drop this on that same response line. So for most of the formations here in the Powder River Basin, this is a sandstone, so that's why I'm putting this as a sandstone matrix and a sandstone clean one point. And then we need to decide where to drop our clay point. Now, ideally, you would have some XRF or XRD data to help you calibrate what type of clay it is that you have. And you might say, oh, I know that I have kaolinite, or I know that I have, some mixed system that's between kaolinite and schmectite, and you would know where to drop this. I'm going to put this on the kaolinite line here. And that, and now I have this V-clay interpretation, which would be fine, but I do have a few limestones in here, specifically the Niobrara formation here. It's a limey marl, and so I want to account for that. So I'm just going to come here, I'm going to select my Niobrara, and now what I'm going to do is, because that has more of a limestone matrix, is I'm going to drop my matrix point and my clean one point here on the higher porosity part of that trend. I'm going to leave my clay exactly where it's at. So if I were to turn on all my formations again, one of the things that I want you to notice here is that I've left my clays the same for both of these, and that's because I in general think that the clay mineralogy hasn't changed too much in our formations of interest here. Note that we have different matrix points for our sandstone units and our limestone units, as well as different clean points for our sandstone and our limestone units. So I just wanted you to see that. And that is how we set our V-clay from neutron density. And that is reflected here in this red curve. You may have noticed it moving while I was adjusting the endpoints. All right, so once we have that, now we want to set some of the other methods. So let's look at some of our single clay indicator methods. And specifically, I'm going to start off by focusing on the gamma ray. So I want to make this big enough so that you all can see it. So I'm going to make, first of all, the scale wider, but I'm also going to make the track wider here. All right, now that I've done that, let's take a look. So when we zoom out, what we can see is that our gamma ray is way too high. Our V-clay from gamma ray, that is. So why is that? It's because we need to adjust our clean and clay endpoints to better match our data in this area. So let's start off, we're just going to put a value in for gamma ray clean and gamma ray clay. We're just going to put that in our default. And I happen to know the values around here, but we could also get those from roughly looking at the curves. And now we want to calibrate ourselves in. So here, we're going to start off by looking at the Lewis formation here and say, all right, what do we have to do to get a match? Well, here on the low end, we need to adjust that just a little bit to match better on the low end. We're still missing on the high side here, so we want to slide that out until now we get that better match. Same thing up here. We don't have a lot of room where we're overlapping with our neutron and density curves here, but we can still do a little bit of calibration there. And we'll go through and we'll do this on a zone by zone basis until we have the match that we are looking for here. Now, you'll notice in some formations, like here in the Parkman, I'm able to achieve a match between my two V-clay methods over part of the section, but not over the other part. And that's because somewhere in here there's a bit of a lithology change, and you would actually want to add a subdivision here so you could calibrate those parameters a little more closely. Now here you'll notice that we have the organic shells of the Niobrara formation. So here our gamma ray is much hotter, and that's because we have uranium that gets associated with the organic material. And so we're going to need to put a much higher gamma ray clean and gamma ray clay here. And note that in organic shells, you're never going to achieve a really high quality match. And in some shells, like, let's say the Woodford or the Bakken, where the values can be exceedingly high, you're probably not going to want to use a V-clay from gamma ray method at all. But here, where they're a bit less organic, not quite as hot, you're going to be able to get an okay match in there. And then we have our V-clay from gamma ray. Now, I did mention there are other single clay indicators out there. So, for example, we have V-clay from SP. And I want to show you this real quickly, and then we can decide whether or not we want to use it. But let's come up here to kind of a more traditional sandstone unit like the Teapot and Parkman formations. So let's say I wanted to use the V-clay from SP in those, and I'm going to change my scale so we can get a little bit more resolution here. So let's say we want to go from, I don't know, minus 50 to 50. All right, now that we can see that, now what do we need to do? Well, we want to try to match this V-clay from SP here, and we can read this value. It's about minus 25, so let's set our default here at about minus 45. Okay, that's pulling us down on the low end. On the high end, the value is right about 0 because we've already baselined our SP. So let's set that at about 10 to get started. All right, and now what we're going to have to do is we're going to have to come through and adjust that, and we can manually drag and drop these. So I'm going to adjust the low end first to where I get a match there. And we see that the high end I'm okay on. We're going to repeat this process for the Parkman. Going to obtain that match on the low end, and then we're going to try to get a little bit better of a match on the high end here. And it takes a couple of rounds of iteration. Now, what is this showing us? And what are some of the differences here? Well, remember that the SP, just due to what that tool is reading, it's not actually measuring clay volume. I mean, none of these tools are measuring clay volume. They're all measuring various properties. Gamma ray is measuring the naturally occurring radioactivity. SP is more of an indicator of permeability. And what is it we see here is that where we have the cleanest, highest porosity parts of the teapot formation, we get, you know, a pretty reasonable match in here. You know, but it's not a great match, and it doesn't seem to give us the same resolution that we get from the V-clay from gamma ray or the V-clay from neutron density. And it's really the same here in the Parkman formation. It serves as a good qualitative measure, but it may not be giving us, you know, a real quantitative measure. You know, of course, we are assigning a number to it, a value to it, but you'll notice that the resolution isn't nearly as high, and that's just because it's not as sensitive. All right, so once we have done this, I'm going to decide that we actually don't want to use SP here, so we're going to turn off those two methods. And the final thing that we'll need to decide is now that we have these two measures of V-clay, one from neutron density and one from gamma ray, how do we arrive at our final clay volume curve? Well, there are two options I'm going to throw out here to you. The first option, which is the one that I normally take, and I think a lot of my fellow petrophysicists generally take, which is to use the minimum of the two methods that we've selected. So what is the one that's giving us the lowest clay volume? Or we can take an average of these. Now, of course, you know, the one when you're taking the minimum is going to be lower than the average by default. Why is it that we would take the minimum instead of the average? Well, personally, I see two reasons for this. One is when you have varying lithologies and you have things like dolomites, especially, a lot of times the V-clay from neutron density will overestimate the clay volume in a dolomite relative to the gamma ray. And often in sandstones, especially if you have a bit of a dirty sand or a sand that's a bit feldspathic or arcosic, the gamma ray will overestimate the clay volume relative to the neutron density method. So I think those are both good arguments for taking the minimum. The other is that if you go through and you're going to be applying cutoffs to these and making gross reservoir, net reservoir, etc. I don't think there's a lot of harm in maybe having a bit lower clay volume in your interpretation by using that minimum method, because we can always try to whittle that down later through the use of our porosity and saturation cutoffs that we'll apply. All right, so that is it. That is how you can interpret clay volume using both single clay and dual clay indicators. What I showed you is specific to Danomics, and we have a lot of methods that are designed to make this fast and easy for you. If you'd like to learn more, just let us know. Send us an email at sales@danomics.com. Thanks.